So the optimal transport problem can be written as this one. Wasserstein distance between two measures, probability distributions, is the minimization of the inner product of two matrices. You know, matrix A and B, you can define the inner product by, for example, trace of A transpose B. So this is how you define the inner product. And so you want to minimize P and MXY. This is the, it's a linear objective and linear constraint. So you can handle it, in linear programming, everything usually goes at the corners, the solution at the corners, and you want to minimize this. You want to minimize, so if this is MXY, this is perpendicular to that, and this is your point, which is the optimal points, and this point is a matrix. This point is a matrix because your manifold is not usual manifold. Is each point? It's a Stiefel manifold, and so each point is a matrix, and you find that, but it is very difficult, and solutions are unstable, not always unique, and also this one is not differentiable, and all those problems leads to think about the fact that we need to regularize them. So just one way of regularization is that, let's say we stick to Gaussian approximation. Just Gaussian approximation. And so there are many ways to regularize. One way is Gaussian approximation. And one remark is that if omega is RD, your cost function is just the distance between x and y, and so your measures are just normal distributions, normal distribution with mean m mu and variance. This is the covariance matrix, and also for class B, again it's just a normal distribution, m nu and covariance and sigma nu, and so then WW, the Wasserstein distance between mu and v, it becomes very interesting because it's just the difference between, this is the idea in linear discriminant analysis, that you want to maximize the distance between the mean of two classes. And you see why linear discriminant analysis is just a special case of Wasserstein discriminant analysis. This one plus b of sigma mu and sigma nu, where b is this matrix, and of course you can say that this one is trace of sigma mu plus sigma nu minus 2 sigma mu half sigma nu sigma mu And so this is just a classic. And another idea for regularization to overcome this problem that your optimization is hard is just stick to a k-dimensional subspace. So we call it k-dimensional or robust projections. Robust projections. So you project your distribution to this hyperplane, let's say, and this is E transpose push forward of mu. So your Wasserstein subject to k-dimensional, and between these measures mu and nu is just the maximize WP of 2. When you push forward to that becomes mu and E transpose nu. And finally, we have entropic regularization that we care very much because it leads to very good and scalable algorithm. That's why we are interested. Regularization. We want to ask optimal transport to be blurrier by using this gamma. So again, your Wasserstein distance is that it's inner product of M and Y, but you add this regularization term, gamma, which is greater than equal to 0, and so this is your Wasserstein distance between mu and. Note that the unique optimal solution happens because of strong concavity of this entropy. And so for fast scalable algorithm, you need this proposition that if P gamma is arg mean of inner product of M and XY minus gamma E of P, then such that P of gamma is diagonal of U, K diagonal of nu, where K is now e to the power of minus mxy y. And it has a great solution, very fast solution, because you can use Sinkhorn fixed point theorem, and that's why you have Sinkhorn algorithm. So it's an iterative approach to find the answer. So this problem has no worry because it has a great solution by the Sinkhorn algorithm based on Sinkhorn fixed point theorem, Sinkhorn's algorithm. And let's start by just talking about why Wasserstein discriminant analysis is better than Mahalanobis metric learning, and also it is better than Fisher discriminant analysis. So Wasserstein discriminant analysis is better because in Mahalanobis metric learning, this is Mahalanobis metric learning, this is the same approach of Fisher, but we are using local information, local interactions between points. But in Fisher discriminant analysis, I said you want to maximize the difference between those, the mean of two classes, and so it's a global interaction So it's a global interaction between points. But Wasserstein discriminant analysis, the idea is to combine the global properties of this algorithm and the local properties of MML algorithm. So this one is a combination of local and global. That's why it is the generalization of Fisher discriminant analysis. So Wasserstein discriminant analysis is a generalization of Fisher discriminant analysis. So we want to find this matrix which reduces the dimension from D to P, and P is your feature size. The reduced size is very, very less than your original size of features. We want to maximize the sum of all distances, between pairs of samples from different classes, C and C prime, while minimizing the sum of all distances. You want also to minimize the sum of all distances between pairs, so within the same class C. So again, the same objective, the same bi-objective, but with a different tool. So that's why when we have a multimodal distribution, performance of FDA is terrible, this one is bad, and this one is better. So two things we should care about. First, all points in one class are matched to all points to another class. This is the global constraint, which is satisfied by marginal constraints in that coupling. The second one is that points in one class are matched only to few similar points of the other class. And this is the local constraint. And so the function of local cost, the distance, you want to you have a metric, you have a distance function of local costs. So we try to by adopting the ratio formulation of Fisher discriminant analysis, which was maximizing. So we adopted to our new formulation based on Wasserstein distance. So now we just say it is the sum of Wasserstein, because you have each pair of classes. It's not just two classes. For all of the combination of these classes, you need to know the Wasserstein. So that's why you are summing over all of these combinations. Wasserstein distance between PXC and PXC prime. This one divided by for within class, which is again Wasserstein distance between PXC and PXC. So this is within class. So P is a P by D, I said. X is a D by N. Machine learning guys say it is D by N. Statisticians say it is N by D. So let's say, because this paper is published in Journal of Machine Learning, let's say it is D by N. And so the multiplication is P by N. So it's a matrix of projected samples. And the Wasserstein distance between any matrix X and Z Z is matrix, X is matrix. So the Wasserstein between them is just the sum of I of j, T star I and j, norm of xi minus zj squared. So, and also T is the coordinates of entropic regularization that I just mentioned. This is the Tij is coordinates of entropic regularized optimal transport matrix. You should notice that if lambda is too small, then WDA is just Fisher discriminant analysis. It converges to solution to that. And if lambda is large, so it is so Wasserstein discriminant analysis split parts distributions of classes by maximizing their optimal transport distance. And so you want to empirically calculate them. So let's say so everything is discretization and empirical things. I have done this before, but let's just review that. So now UNM is polytope of all n by m non-negative matrices. And this is inside n by m. T should satisfy T transpose 1m is and so because their row and column marginals are equal to n and m respectively. So the regularized Wasserstein distance, of course, as I said, the inner product of two matrices is just trace of A transpose B. I think it's Frobenius dot product of matrices. And for lambda greater than equal to 0, Wasserstein distance of two measures mu and v by definition. Now we have two matrices, as I said. So instead of measures mu and v, we have matrix x and z, because you have discretized it. And this is the inner product of m and t. So T lambda is the solution of entropy smooth optimal transport problem. So T lambda, by definition, is arg mean over all u over all t of lambda t m x z minus the entropy of T, which is seen as discrete joint probability distribution. And this is solved using Sinkhorn. I said that it is easy. You can solve it using fixed point iterations. So I'm just reviewing it. And it is an algorithm that this is the solution diagonal of V, which is this one. This is the element-wise multiplications of the three matrices. And so, because it's an iterative process, because you are doing fixed point theorem, you're using that. So in this process, VK is 1m divided by K transpose UK minus 1, and UK is 1n